Before we proceed with the demonstration of electric field lines, let us have another example problem for electric fields. A 2 nanocoulomb charge was placed at a position of 0 meter 4 meters. What is the magnitude of the electric field at position 2 meters 0 meter? In this problem, the charge and the position are given. The position at which the electric field should be measured is also given. Since the coordinates of the distance between charge are given, we can use the Pythagorean theorem to calculate r from the source charge. From this graph, our x-coordinate is 2, while y is 4 meters. Substituting these in our Pythagorean theorem, we will have r is equal to 4.47 meters. Now that we have all the required variables, we will substitute these in our equation. E is equal to k multiplied by absolute value of q over r squared. Let us substitute the values, compute this in your calculator as follows, and the value we will get is 0.90 Newton over Coulomb. For your assignment problem, try to solve this. We will be solving this in our next synchronous session. From the previous lesson, we have learned that vectors can be illustrated as arrows. In the case of electric field, since its variables are both vectors, therefore electric field is a vector quantity. We are going to show it using electric field lines. To illustrate the electric field lines of single charges, we are going to draw rays depending on the charge that is being illustrated. For a positive charge, the field lines should be directed away from the charge, while for a negative charge, the field lines will be directed towards it. In the case of dipoles or charges that are interacting with one another, we have to determine first whether the charges are attractive or repulsive. There are 3 possible ways on how we can draw dipoles. Number 1 is attractive, where positive charge attracts negative charge. Again, the arrows for negative charge are represented away from the charge, while towards for the positive charge. We can simply combine these two to present attractive forces between them. Number 2 is repulsive force for 2 positive charges. Arrows for both of these charges are drawn away from charge, and so it can be represented as this. The electric field present exhibit repulsive forces. And lastly, repulsive force for 2 negative charged particles, where the arrows representing electric field is towards the charged object. It is important as well to consider the head of the arrows where the electric field is going. This is what makes us aware which is negatively charged and positively charged. Based from the illustration that we have, I will present you statements and identify whether these are true or false about electric field lines. In general, we have 3 basic rules in drawing electric field lines. First, field lines emanate from the positive charge and terminate to the negative charges. Second, field lines do not intersect at one point. Instead, they only meet if the force between the charges is attractive. And lastly, the density of lines or the number of lines per space represents the strength of the field. In other words, the more lines that we draw, we would mean stronger magnetic field. If the lines are equally spaced, it can be said that the electric field is uniform. In the next video, we will talk about the relationship of electric field and electric force. But that is all for this video. I am Gilmar De Castro, and see you in the next video.